Implementing a serverless GraphQL API with AWS Lambda and Application Load Balancer using Terraform. This podcast is brought to you by Business Compass LLC. We are an Amazon Web Services advanced consulting partner. We build and migrate workloads to Amazon Cloud. Our website is businesscompassllc.com. Our phone number is 973-638-2228. Our email address is contact@businesscompassllc.us. Introduction. GraphQL has become famous for APIs due to its flexibility and efficiency. Coupled with AWS Lambda, it provides a robust serverless architecture that can scale automatically and reduce costs. When paired with an AWS Application Load Balancer, ALB, it ensures high availability and improved performance. In this podcast, we will explore the advantages and disadvantages of this setup and provide a step-by-step tutorial on how to implement a GraphQL Lambda function behind an ALB using Terraform. Advantages of using a GraphQL Lambda function with an AWS Application Load Balancer. Scalability. AWS Lambda automatically scales your GraphQL API based on the incoming traffic. This ensures that your application can handle numerous requests without manual intervention. Cost efficiency. With AWS Lambda, you only pay for the compute time you consume, which can result in significant cost savings compared to traditional server-based architectures. High availability. The AWS Application Load Balancer distributes incoming traffic across multiple targets, ensuring high availability and reliability. Reduced operational overhead. Managing servers and infrastructure is simplified, as AWS handles most operational tasks, such as scaling, patching, and maintenance. Seamless integration. The combination of GraphQL, AWS Lambda, and ALB integrates seamlessly with other AWS services, providing a robust and comprehensive solution for your application needs. Disadvantages of using a GraphQL Lambda function with an AWS Application Load Balancer. Cold starts. AWS Lambda functions can experience cold starts, which may introduce latency during the initial invocation. Complexity. Setting up and configuring Lambda functions with an ALB using Terraform can be complex, especially for beginners. Resource limits. AWS Lambda has certain limitations on execution time and memory, which might not be suitable for all workloads. Debugging and monitoring. Debugging serverless functions can be more challenging than figuring out traditional servers, requiring additional tools and practices for effective monitoring. How to implement a GraphQL Lambda function behind an AWS Application Load Balancer using Terraform. Prerequisites. AWS account. Terraform installed. Basic knowledge of AWS Lambda, ALB, and Terraform. Step 1. Set up the Terraform configuration. Create a new directory for your Terraform configuration and navigate to it. Inside the directory, create a file named main.tf and add the following configuration. Provider AWS. Region equals US East 1. Resource AWS _ Lambda _ function GraphQL _ function. Function _ name equals GraphQL _ Lambda. Runtime equals Node.js 14.x. Handler equals index.handler. Role equals AWS _EAM _ role.lambda_exec.arn. File name equals path//your/lambda/deployment/package.zip. Resource AWS _EAM _ role lambda _exec. Name equals lambda _exec _ role. Assume _role _ policy equals JSON encode. Version equals October 17, 2012. Statement equals. Action equals STS assume role. Effect equals allow. Principal equals. Service equals lambda.amazonoz.com. Resource AWS _EAM _ role _ policy _ attachment, lambda _exec _ policy. Role equals AWS _EAM _ role.lambda _exec.name. Policy _ARN equals ARN. AWS, IAM, AWS, policy/service role/os lambda basic execution role. Resource AWS _ GraphQL _ alb. Name equals GraphQL alb. Internal equals false. Load underscore balancer underscore type equals application. Security underscore groups equals AWS underscore security underscore group dot alb underscore sg dot id subnets equals AWS underscore subnet dot public ID. Resource AWS underscore security underscore group alb underscore sg. Name equals alb underscore sg. Description equals allow inbound HTTP traffic. VPC underscore ID equals AWS underscore VPC dot main dot ID. Ingress. From underscore port equals 80. To underscore port equals 80. Protocol equals TCP. CIDR underscore blocks equals 0.0.0.0.0.00. Egress. From underscore port equals 0. To underscore port equals 0. Protocol equals -1. CIDR underscore blocks equals 0.0.0.0.000. Resource AWS underscore pound underscore target underscore group GraphQL underscore TG. Name equals GraphQL TG. Port equals 80. Protocol equals HTTP. VPC underscore ID equals AWS underscore VPC dot main dot ID. Health underscore check. Path equals /health. Interval equals 30. Timeout equals 5. Healthy underscore threshold equals 5. Unhealthy underscore threshold equals 2. Resource AWS underscore pound underscore listener HTTP. Load underscore balancer underscore arn equals AWS underscore pound dot GraphQL underscore alb dot arn. Port equals 80. Protocol equals HTTP. Default underscore action. Type equals forward. Target underscore group underscore arn equals AWS underscore pound underscore target underscore group dot GraphQL underscore TG dot arn. Resource AWS underscore lambda underscore permission alb. Statement underscore ed equals allow execution from alb. Action equals lambda invoke function. Function underscore name equals AWS underscore lambda underscore function dot GraphQL underscore function dot function underscore name. Principal equals elastic load balancing dot amazonoz.com. Source underscore arn equals AWS underscore pound dot GraphQL underscore alb dot arn. Resource AWS underscore VPC main. CIDR underscore block equals 10.0.0.016. Resource AWS underscore subnet public. Count equals 2. VPC underscore ID equals AWS underscore VPC dot main dot ID. CIDR underscore block equals 10.0.1.024. Availability underscore zone equals data.aws underscore availability underscore zones dot available dot names count dot index. Data AWS underscore availability underscore zones available. Step 2. Deploy the resources. Initialize the Terraform configuration. Terraform init. Apply the configuration. Terraform apply. Confirm the apply action when prompted. Step 3. Create the Lambda deployment package. Ensure your GraphQL Lambda function is packaged correctly. For a Node.js example, your index.js might look like this. Const Apollo server GQL equals require Apollo server Lambda. Const type defs equals GQL. Type query. Hello, string. Semicolon. Const resolvers equals. Query. Hello equals greater than hello, world. Semicolon. Const server equals new Apollo server type defs, resolvers. Exports.handler equals server.createHandler. Package your Lambda function. Zip our function.zip. Update the file name path in the Terraform configuration to point to this function.zip file. Step 4. Testing. Once the resources are deployed, the ALB will have a DNS name. You can use this DNS name to test your GraphQL API conclusion. Implementing a GraphQL Lambda function behind an AWS Application Load Balancer using Terraform offers numerous benefits, such as scalability, cost efficiency, and high availability. However, it also comes with challenges, such as cold starts and complexity in setup. By following this podcast, You can leverage the power of AWS and Terraform to build a robust and scalable GraphQL API. Thank you for listening to our podcast. Please share this podcast, visit our website, and follow our social media links.